Hey everyone, this is a 3D scan of a barn structure sent in by one of our viewers. He is planning to renovate it and transform the old barn into a residential house. The house has already been designed by his architect and the model was created in SketchUp. The problem is that it was built on inaccurate measurements, so they can't move forward with the construction. So he scanned the job site with his SHARE S20 LiDAR scanner and sent me the data. My task is to turn that scan into a CAD model so the architect can correct the design and move forward with the construction. In this video, I walk you through the workflow of creating a structural 3D CAD model from LiDAR scan data using BricsCAD. I will also show how to convert that 3D model into 2D CAD drawings for architectural use. Construction has already started on the site and there are quite a few obstructions for the scanner. This level of obstruction is pretty normal, and to capture as much of the main structure as possible, you need to move around to different positions to eliminate blind spots. The black steel frame you see is the main portal frame of the building and is the key dimensions for modeling. The red painted sections are the interior drywall frames, which will be removed and excluded from the model. The scan was done both inside and outside the barn, which allows me to define the wall thickness accurately. The scanning took about 10 minutes. The black main structure isn't fully captured because parts of it were blocked. That makes this scan more challenging to reverse. To handle it successfully, you need some basic construction knowledge. AI tool that automatically convert point clouds to CAD won't work in this situation. While I was editing this video, Chad sent me the new Point Cloud Studio to try out. This version includes an AI feature that can convert interior scan data into a 2D CAD floor plan. For example, this small apartment took about 3 minutes to process with the GPU running at full capacity the whole time, so it's clearly a purely AI-driven function. The AI generates walls, doors, and windows in 2D vector CAD, but since this apartment isn't empty and has furniture, the floor plan isn't accurate. Many of the walls, doors, and windows are misplaced. About 40% of it is wrong. Human judgment is still an essential part of reverse engineering. If I kept using this AI-generated floor plan, I would end up spending more time fixing the errors than if I just redraw it accurately with 3D modeling in a professional CAD tool. Here I'm testing another example, a clean scan of a 3-story house with no curtains, door panels, furniture, or windows. This should be the ideal condition for the AI engine. And here is the result. The walls, windows, and doors are misplaced. About 40% of it is wrong, even under the easiest conditions. The floor ended up being 600mm too wide. This isn't the first time I have tried AI tools like this. They all produce similar results, and none of them actually save time when it comes to CAD modeling. AI tools like this still need far more training data, probably over 100,000 examples, and even then they won't be 100% reliable. Buildings are complex human creations shaped by years of architectural experience, and that's something AI will never fully replicate. There is another tool that lets you create a cross-section of the point cloud and automatically extract the sketch boundary. You will also find this feature in AutoCAD, BricsCAD, and Cloud Compare. The result is actually worse than the AI floor plan too, because the cross-section only uses a thin slice of the point cloud. It tries to generate lines wherever it can. To get accurate results, you need a perfectly clean scan with no obstructions and nothing but walls. Even then, the wall lines end up misaligned compared to manual tracing. There is also a new CAD tool that lets you trace lines manually. This is a very useful feature. It works better than the AI tools and is perfect for quick sketches. Plus, you can export the file directly in DWG format. This is the best addition I see in this update. Another welcome feature in this version is the ability to set GPS elevation. Previously, you were stuck with ellipsoidal height, but now you can switch it to the mean sea level. Okay, that's not all. Another great feature in this update is the ability to align scan data directly. You can use the 3-point alignment tool or align one side of the scan to the x-axis by picking 2 points. This eliminates the need to take the data into Cloud Compare for alignment. Now let's move to the real-world practical scan-to-CAD workflow. Reverse engineering in BricsCAD. For this project, I'll be working in millimeters as the unit. Before I start modeling, I will align the longer side of the wall to the x-axis by pairing these 2 points to a horizontal line. I will also align the point cloud along the y-axis so the building stands perfectly upright. And finally, I will align the floor to the x-axis. That means there are 3 planes that need to be level before we can begin modeling. Then I draw a line between these 2 columns and use the center of that line to move the point cloud to the origin point. If you skip this step, you will quickly realize you can't continue or finish the modeling. After tracing the lines along the floor edge, I will extrude the first solid. Some parts of the floor have a lower step, so I will create a profile to cut those areas down. I can clearly see the floor step in the point cloud, which makes it easy to locate both its position and the depth. Next, I will locate the center line of the I-beam in the portal frame. Since the steel frame appears in black, I may need to change the viewport background color to make it stand out clearly. Next, I will crop out the best portion of the point cloud to extract the column and beam size. This column has a depth of 200 mm, so its center is located 100 mm from the edge. For the beam, the depth is 300 mm. Because this portal frame is symmetrical, I will create a mirror line and use it to mirror the beam axis. BricsCAD BIM includes a structural steel frame feature that lets you select a profile and apply it directly onto the center line. It also includes a function to automatically join steel members together, offering various connection types. For extending a steel member, you can simply use the standard push-pull command. Now moving to the larger section of the barn, the steel member is one size larger than the previous one, and you can easily adjust the steel size from the property panel. The scan data in this area is incomplete, so I will transfer the column position from the next bay. Next, I will move the columns into place. Once the columns are repositioned, I need to rerun the steel joint command because the roof beam remains in its original location. Next, I will create a block of the portal frame and copy it into position, aligning it with the visible point cloud. Each bay here has a slight difference in length, about 2 or 3 centimeters. There are inventories stacked against the walls, which make it difficult to locate the exact column position. Here at the last bay, I'm trying to locate the beam position, but it isn't visible in the scan. Instead, only drywall structures are present, so I went back into Point Cloud Studio and checked the panoramic photo shots. From there, I was able to spot the beam sticking out from beneath the ceiling. Looking back at the point cloud, I can now see the beam, so I will copy the portal frame and move it into this location, aligning it with the scan. The columns have been concealed inside the drywall, which is why they are invisible in the scan. Next, I'm adding cross braces to the model. I will use an angle steel profile with a size of 150 mm. Cross bracing is a tension-only structural member. It provides lateral support when a wind load acts perpendicular to the portal frame. Usually, cross bracing is placed at the center or along the lower chord of the beam. Now I'm adding purlins. Purlins are used to support the roof cladding. In this case, a metal sheeting with a spacing of 1 meter. The steel profiles most commonly used for purlins are C-shape, light lip channels, or U-shape sections. Now I'm adding drywall panels and cutting out the door opening. This panel is used to conceal the metal roof sheeting and the rain gutter from view. It's a common practice in commercial and industrial buildings. I noticed some glass wool in the scan data. It's likely placed between the outer and inner drywall layers, and here the wall thickness is around 20 centimeters. Glass wool provides thermal insulation only. If sound insulation is also required, rock wool should be used instead. Metal sheeting roofs usually generate a loud noise during rainfall. To reduce sound transmission, materials like rock wool or heavy gypsum board can be used. Now I'm using a different approach to model the drywall panel. First, I will extrude the line into a surface and then add thickness to it. After that, I use another surface to trim it so it fits the ceiling profile. This method is also a shortcut for modeling walls quickly. It requires fewer mouse clicks and gets the job done faster. Now I'm modeling the ceiling panel using the same technique. I start with lines, extrude them into a surface, thicken it into a solid, and then trim it to fit the ceiling profile. Now I'm modeling the drywall that conceals the steel columns. Now I'm modeling the mezzanine floor slab. The floor slab is supported with a steel joist, so it occupies more volume in the structural model. And here's how I model the spiral staircase. I start with the central column, then create the first step at the lowest position. To array the staircase step, I will create a helix as the part around the central columns. Then I use the array along path command to generate the staircase step along the helix. And here's the final wall, which I believe is the HVAC room. The modeling took about 4 hours and the file size is only 1.4 megabytes. Once you have a 3D model, you can automatically generate 2D drawings using the base view command. You can create front, side, and section views with just a few clicks. When the 3D model is adjusted, the 2D drawings adapt automatically. This is the major advantage of generating 2D drawing from a 3D model. They are faster to produce and more accurate. I've been using this approach for over 27 years with Autodesk Inventor. This is also the best approach for converting LiDAR scans into CAD drawings. I was able to generate 8 A3 size drawings sheets in less than 3 minutes. You can export the sheets as a 2D CAD drawings and no one will know they were generated from a 3D model. Here's my tutorial modeling the barn structure from LiDAR scan data. AI is still a long way from being truly useful in CAD modeling. I have been following its development for years, but it still doesn't deliver a real usable results. Thanks you guys for watching. I'll see you in the next video.